Okay, so let's start the class today. So first, the reminder that we'll have exam 1 next week. Okay, so you should come to school, and I will email you which room you should go to. And this is basically the material that will be covered in the exam 1. Okay, so basically chapter 2, 3, 4, 5, 6, and homework from 1, 2, 3, 4, and some other material covered in during the lecture. Okay. See. Okay. So next we will have the exam. Okay, so So again, let's just start from review in some of the homework. Okay. So in homework 3, there's a problem about the entropy increase. Okay. So that means we want to show if the entropy will increase as we increase the time. Okay. Okay. So let me see, what do we want to say here? One moment. Okay, so in general, for a closed system, the entropy does not increase. Right? Okay. So, but however, we are going to show that if we consider the diffusion equation. Okay. In this case, the entropy will increase. Okay, so what's the diffusion equation? So diffusion equation tells us that partial rho partial t equals to some diffusion constant multiplied by the gradient of rho. Okay. Okay, so now from this entropy, how do we calculate the entropy with this? We consider this rho as the probability density. Okay. So in this case, we are going to use this non-equilibrium definition of the entropy, which is the rho log rho and the integration. This is a continuous variable. Okay. So now we can plot this equation to check what's the time derivative of the entropy. Okay. So by definition, we are going to have, so we can move this, we can set this, we can forget about this Boltzmann constant. Since it's just a constant, we are going to just basically to check the sign of this equation. Okay, so now then this becomes the partial derivative, and you have to apply the chain rule. Let's put it this way. So you first apply this time derivative to the rho, and then you apply this time derivative to the log rho, so you have 1 over rho, and then partial rho, partial t. Okay. So now for this, I can so now there are two terms. I can the second term. So this rho and rho 1 over rho cancel. Okay. So the second term, basically I can now take this time derivative outside the integral. Okay, I can write this. Okay, so now I move this outside back again. Okay, but I know my probability density is normalized. So that means this is nothing but they should normalize to 1. So if you take a time derivative, it should be 0. Okay. Okay. So about the second term, the first term. So it's a diffusion constant. Okay. And I don't quite like this log rho, right? Because I don't know how to deal with. Right. So one typical way to deal with this is to perform integration by part. Right. So we can think about a function partial rho partial x log rho. So if I take the derivative of this is the second derivative plus this partial rho partial x 1 over rho. Right? So then I can okay. So that means this is something like the partial rho partial x log rho. Now I have this boundary plus the term like I do this. Okay, now here this is a partial rho partial x. Okay. Okay, so I don't remember this formula for the integration by part. So I just try to construct some function. When I take a derivative, if first spit out the term I have. Okay, and then there are some extra terms. So I have to subtract this extra term. Okay. So now if you look at the problem, it say this density and this gradient die rapidly away. Okay, so you can think about this integration is from minus infinity to infinity. Okay, so this what is the meaning of this condition? So usually I assume this probability density is local. It's not something that go to. It's still finite when you go to infinity. So at the infinity, you should go back to 0 quick enough. Okay, so in that case, this partial rho partial x multiplied log rho at the infinity should give us 0. Okay, so I have only this term left. Okay, and now this term I can easily group them together. So I can show that this is positive. Okay, so this is something square, so this is positive. And I know the probability density is positive, so that tells us this integration must be positive. So that means my entropy change is always a positive number. Okay, so the question is why? Okay, so basically, if you this is coming from, if you go back to the derivation of the diffusion equation. Okay, so then this is a step that we sort of assume that there's some long wavelength limit. Basically, we are averaging over the small scale. Okay, so basically we are doing some coarse graining. And so in that way we get some effective theory. Okay, you think about some Brownian motion type or random walk type of behavior. Okay, so now, but if you look at the large scale and you sort of cross grain the detail, and you obtain some effective theory at the long wavelength limit. Okay, so this cross graining basically essentially means that you throw away some information. So that there are some detail that you don't care about, right? So you just to perform average. So remember that this diffusion constant is sort of come from the expansion, and you also have to integrate over your probability density. And so basically you forget about some detailed information. Okay. And as we mentioned, the entropy can be sort of something related to information, right? So if you keep throw away you have less and less information, so that means it's you can think it's more, you got more or more disorder or more disinformation, so your entropy will increase. Okay. So the lesson for this homework is if you calculate the full dynamics, right, either by quantum Hamiltonian or classical Hamiltonian, and so you have if you think about you solving a Newtonian equation or Hamiltonian equation, so suppose I give you initial condition and your Hamiltonian, then you know all the information at any time. Okay, so in this case, your entropy will be a constant. Okay. Only if you do certain cross-graining. Okay, so in our kind of canonical example, what happened there? That we have another system that we call Bath, right? So we trace over the degree of freedom of the Bath. Okay, so when we do that, we sort of throw away some information. Okay, so usually if you do certain cross-graining, then you throw away some information, then your entropy will increase. However, if you do for a closed system, and then you perform exact dynamics, then entropy will be constant. Okay, and the next is a simple exercise for this Gibbs factor. Okay, so this when I have a classical ideal gas undistinguishable, we talk about this. If I only think about the configuration space, that is not the momentum, right? So then the entropy is v to the power m, take a log, okay? But I have to introduce this Gibbs factor. Okay, so in this case, so for especially for the undistinguishable particles. Okay, so I want to relate it this to entropy, so it's very easy. So we just take a Stirling approximation. So this will be n log n. So this will be n log v minus n log n plus n. Okay. Okay. So then you can write this nkb 1 plus log v divided by n. Okay. So v divided by n basically is something related to your density. Okay. So if you want to further combine this to a single equation, what you can do is to imagine that this 1 is nothing but the log of e. Right? E is our constant, right? So if you write in this way, you can actually absorb this into. Okay. So now if we look at the ideal gas, the entropy we know has this form. Right? Okay, so this is okay. So now so this part comes from the configuration space. So I can consider this is a configuration entropy. Okay, so I just want to see what is I can separate this entropy of the ideal gas. Okay, so I think I can take 1 minus log rho, and then I still have 3 half and minus log lambda third. Okay, and I know this is rho. This is minus rho. I can take a minus sign out, and this becomes n divided by b, and this will be minus log rho. Okay, so the first two terms is nothing but our configuration entropy, and then I have this remaining terms as 3/2 minus log. Okay, so this is just a simple separation of your entropy. Okay, so now if we move to problem 520. Okay, so this just need to exercise the definition of entropy. Okay, for A, okay, so then A, there's a discrete one. Okay, so I have a 3 possible outcome. So the outcome can be 1 or 2 or 3. Okay, and the corresponding probability is 1/2, 1/4, 1/4. Okay. So for this discrete set of discrete probability, I can define the entropy as sum over possible outcome, the probability, and the log of a probability. Okay. So then I can let's put this in. So I have probably 1/2 log of 1/2 plus 1/4 log 1/4 plus 1/4 log 1/4. Okay, simple. So you can get the result. Okay. Okay, so the problem B basically is what happens if you have a probability density. So then you have a probability density that is constant, or you have a probability density that has theta dependence. Okay. Okay, so now here, typically in the spherical let me see. Let me write this so cosine. Let me see, what do I want? Cosine square, I want to have theta of sphere. Why is that? Okay, so then basically you have to perform this definition of entropy, which is the rho log rho. Okay. Okay, so now this is some d here. Yep. So now if we just follow the link, so okay, so so let me see. So why do I want that? So if I have f theta, so f theta, so that means okay, and then we are going to use this measure of the integration. Okay, so now this is a function f theta. Okay, and then we need to integrate over this sphere, and they just thought, let me see. If you use a different measure, what happened? So let's just follow this here for now. So if we just follow the hint, what we should do is something that you have a cosine square theta. Okay, and then you just plug in the two definition of this probability density, and then you can, and then you have to work out the calculus, and then you can get the answer. Okay. So now we want to go to, there are two problems about this rubber band. Okay, so that's the PB 5.112 and also problem 6. Okay, so this is basically something related so-called the entropic force. Okay, so now let's just start from the problem 5.12. Basically, we want to calculate a microcanonical ensemble calculation. Okay, so if you consider microcanonical, basically you want to calculate entropy from the log of the omega function, right? And omega function now, this is a discrete distribution, basically is the number of possible configuration. Okay, so how do I understand this? So I have a, I think about my rubber band as from my polymer. Okay, so I have a segment. Each segment has a length small d. Okay, so I have a totally I have n segment, capital N. Okay, so I can think about this when this is the starting point. Okay, so then just like a random walk, I can go forward or go backward. Okay, and at the end of the day, then I have some total distance capital L. Okay, so if we want, we can put an arrow on it. Okay. So this is a plus 1 and this is the minus 1. Okay. So I can think about I have n plus that go in this way and n minus that go in that way, go back. Okay. So I have a total capital N, which is the sum of n plus and n minus. And what is my total distance L? It will be my n plus minus n minus multiplied by d, which is the length of each segment. Okay, so now if I give you L, then I want to find the number of possible configuration that can give me total length L. Okay, so now this is simple because that means I have to take this out of this capital N segment. I have to take this specific one, n plus. Okay, now come back to here. From those two equations, I can solve for n plus. Okay, and this is 1/2 capital N plus L divided by 2D. So that means m minus okay. So that means if I fix total numbers, if I fix the capital N and the capital L, then I determine n plus, right? So now I can think about this is actually a function of n, L, and n. Okay, so not this. Right? And this is something like m plus n divided by 2 plus L divided by 2D factorial n divided by 2 minus L divided by 2D factorial. Okay. There's no minus here. Okay, so the entropy is nothing but I take a Boltzmann constant multiplied by log of the omega function. Okay, so F okay, so as you can see now, if you this omega function would be this is a function of n, L, and small d. Okay, so now I want to find something that is related to the force. Okay, so now how do I connect this to a force? Okay. Okay, so now I can consider here this is my system. No. Okay, so first I pin the head, the beginning of my rubber band to the wall. Okay, so then I have this. And this is the end, and the total distance is L. Okay, so this is my system. Okay, and then I imagine that I couple the system to a heat bath at the temperature T. Okay, and then reach equilibrium. Okay, so in order for this rubber band to maintain this distance at L, I can imagine that I have to have some force F that pull on rubber. Okay. And then I have I have action, then I have a reaction, right? So if my environment pull on my rubber band, then my rubber band pull on my system F, right? So they will have the same magnitude but different sign, and they act on different system. Okay. So this force act on my base is called the entropic force. Okay, so it's due to entropy. Okay, because my rubber want to maximize the entropy. Because of this, it will exert a force on the base. Okay, so now I want to connect. Remember when we calculate this and we have a system 1 and system 2 and we couple them, we allow them to exchange energy. Okay. And when we reach the equilibrium, then I can define this thermodynamic temperature as the derivative of the entropy with respect to energy. Okay. Okay, so if I took a partial derivative of the entropy of the base to the energy of the base, then I get 1 over the temperature. Okay. Okay, so now, but I want to connect this to F. Okay. Now, if I allow my capital L, so my total length to change, that means I am going to insert energy to the base. Okay, and with proper sign. And I know if I have a force F, and if my distance is dl, then my energy change dE is F dot dl. Okay, and let's have a convention that this is a minus. Okay, so in this case, I can replace this partial E by partial F dot F dl. So that means it's 1 over F and the partial L. Okay. So, but the point is want to get this partial S, partial L. Okay. So the point is this displacement multiplied by the force is related to the energy change, right? So this partial derivative to E, I can connect that to the partial derivative to L. Okay. Now for the system plus base, it's an isolated system. Okay, so it's always important to identify what is sort of the total system that is isolated from everything else. Okay, so for isolated system, we expect that the entropy change, total entropy change, should be 0. So that means if I do the best, and the entropy can be separate into the entropy of the base and the entropy of the rubber band. Okay, and the total change of them will be 0. Okay, so from this equation we find partial S, this is equal to minus F divided by T. Okay. No. Okay, so this is partial L. Okay, so I want to see if I change the rubber band's total length, then the base entropy change base will have certain entropy change, and the rubber band and also have a certain entropy change. Okay, so now I can relate that to the entropy change of S, the partial derivative of S of your rubber band with respect to L. Okay, so that means I want to have a formula for F, which is the time, temperature multiplied by S. Okay, so that's our desired result. Okay, so now if I have an expression for L entropy, then I can perform this partial derivative, right? So now I can use a Stirling formula. Then my entropy of the band, rubber band, is basically Kb n log n. Okay, so this is an approximation, but a very good approximation. Okay. And now I can perform this integral, partial derivative. Okay. And after some algebra, which I'm not going to calculate here, you arrive at this result. Okay. Now consider like a spring constant. So I have a Hooke's law. But Hooke's law applies when you have a total displacement is very small. Okay. So basically, when I want to extract this spring constant, I will consider the limit that the displacement is very small. Okay, so then basically I can consider the limit like my total length is much smaller than the maximum possible total length, which is capital N multiplied by D. Okay, so then basically I can have this is log 1 plus L divided by ND, 1 minus L divided by ND, and then I can treat this L divided by ND to be a small number. Okay, so then what I can get is this is approximate the KBT divided by 2D. And this is basically okay. So the force should be proportional to the spring constant multiplied by L. So that means I can get my constant to be KBT divided by ND squared. Okay. Okay, so roughly speaking, we are calculating the microcanonical ensemble. So the way we do it is we start from omega. We want to calculate omega function somehow. Okay, from omega function I can get entropy. Okay, from entropy I can get like a temperature, everything. Okay, so now if I consider the same problem, but we are sort of switched to a canonical something like a canonical example. Okay. Okay, so here we are going to, but this is not exactly canonical because in canonical example we fix the temperature. But that's like instead of in microcanonical ensemble, we just show there we fix the total part. We basically treat the n as an independent, L total length L as our independent variable. Okay, and we can see that L is basically sort of conjugate to the force. Okay, so we can imagine so that in our typical example, I have the energy. Okay, so I have entropy. Okay, but then I also have a P and V, right? So here is something similar to P and V. So I have a force and I have a length. Okay, so it's similar. Okay, so it's something like we'll fix the temperature and the force. That will be similar to I fix the temperature and the pressure. Okay. So now I have something that fixes the temperature. So I want to write something as a Hamiltonian. Okay. So remember that basically if I have a total Hamiltonian, that can be sum written as a sum of individual, like one particle or one side Hamiltonian. And then my partition function, then typically my partition function can be written as a single partition function to the power of n. Right? So that's okay. So I want to write, and what's Hamiltonian? Hamiltonian essentially is energy. Okay. So the question is, what is the energy if my total length is L? Okay. So now, if I think about, I start from something that has zero total length. Okay. So according to our, and if I have something that has a constant force, and my total displacement is L, right? So my energy will be F multiplied by L. Okay. But now I want to decouple this into a sum of individual Hamiltonian on each segment. Then I can write this as a sum over each segment has a Sn and then multiplied by D. Here the Sn is plus 1 or minus 1. So it's going forward or going backward. So I can write this as summation of Hn, where the Hn is FDSn. Okay. So now my individual partition function is nothing but I have two possibility Sn plus 1 or minus 1. When it is minus, I got Fd divided by kBt. When it is plus, I got the plus Fd divided by kBt. Okay, and my partition function is the product of my single segment partition function, and this is something like a 2 to the cos of Fd divided by kBt to the power of capital N. Okay, okay, so let's take a 10 minutes break and be back at 2:20. Okay, so let's continue. Okay, so basically now we want to change to a different ensemble. Okay, so it's that now basically you allow exchange of energy to the environment, and also you allow you change your length. Okay. Okay, so but then how do I connect this to the how do I connect this to the L? Right. So if I can exchange the volume, so I have certain I imagine that I can get some kind of free energy, and when I take the log of the free energy and then take a certain derivative, I then get the maybe the length L. Okay, right. So now I can think about this L as an expectation value. Okay, so now let's just define some free energy. Okay, so it's free energy is always something log of the partition function. Okay, so now log out this partition function, and then with the KBT. Okay, then I call this my free energy. Okay, and now just plug in our formula. This is something like KBT and log. Okay, when I take a log, so I have a bring down a prefactor n, and then I have a log of the one side partition function. So that would be okay. So now let's just briefly take a partial derivative of this to f. Okay, so the energy change is something like f dot dl. So I know the L and the F are sort of conjugate variable, right? So that means if I want to get L, I probably should take some kind of partial derivative with respect to F. Okay. So now let's check this result and see if this makes sense. Okay, so I have so this will be KBT partial log our partition function partial f. Okay, so now this always bring down a 1 over partition function, so that will serve as our normalization factor. And then I have partial of my partition function to f. Okay. Okay, so but formally, what is my partition function? Okay, so partition function means I sum over S1, S2 to Sn. Okay, and I sum and I have my energy H divided by my energy. Okay, and what is my H? H can be written as Fd sum of n Sn. Okay, So that means if I take a partial derivative with respect to f, the important thing is what do I bring down, right? So basically I bring down the factor of minus d sum over Sn divided by kbt, and this is my weight. Okay, so I can see this kbt factor cancel, okay, and minus cancel. So basically I have 1 over partition function, and I have sum over my segment orientation S1, S2 to S capital N. Okay, and this D multiplied by summation of Sn is nothing but my L. Okay, but this L is a function of S1 to F capital N, and then I have this external Boltzmann weight. Okay, so this is nothing but the definition of the expectation value of my total length, right? So for certain configuration, I got the length, and this is the probability, relative probability of that configuration, and then I divide by normalization of the probability, the partition function, right? So combine all this result, I get this. Okay, so my length expectation value is nothing but my free energy partial derivative with respect to my F. Okay, so now if you plug in our result, you will get something like oh no, there's no minus sign here, and the hyperbolic tangent FD divided by KBT. Okay, so again we want to extract the spring constant, so I want to find the proportional constant that my force is minus kappa multiplied by L. Okay, so that means my 1 over kappa is nothing but partial L partial L. Okay, so that's the partial square. Okay, but essentially I'm interested in the case when I have almost no force, right? If I only perturb around my equilibrium condition, okay, and if you calculate at least this limit is basically something like and you get the same result. So my kappa is kBT divided by ND squared. Right? Okay, so now there's another question that if we increase the rubber band temperature, would the rubber band contract or extend? Okay, we can look at this expression for the spring constant. So if I increase the temperature, since my spring constant is proportional to T, so if I increase the temperature, my spring constant increase. So then maybe my that means my rubber band will contract. Okay, so can I derive this in a more like formal way? Okay, so then for this kind of calculation, we are going to need the result from our other homework. That front one is the triple product relation. Okay, so I have a rho x, rho y, f, rho y, rho f, x, rho f, rho x, y is minus 1. Okay, so how do I apply this first? Okay, so basically what we want to know is if I increase the temperature, what happened to my length, right? So I calculate this maybe at a fixed f. Okay, so first I'm going to apply this triple product relation. So partial L partial T F and then so this is Y. So I have this partial T partial F at L and then partial F partial L at the T is minus 1. Okay, so first I apply this triple product relation to L. And I can think about this is okay, you can think about anyway. Okay, so basically I have 3. They are related. Okay, so now the second step is I'm going to invert this 2. Okay, so I move, so that means my partial L partial TF is minus 1 over partial T partial F 1 over partial F partial L T. So then I can invert this one to be minus 1 multiplied by partial F partial T. Okay, so I can take the inverse, then basically then this let me see. I want the yes. So I have a partial L partial F T and the partial F partial T L. Okay, so basically I invert this. Okay. Now we have to calculate that the partial L partial F is nothing but my 1 over kappa, the spring constant. Okay, so I know this one. Okay, so I want to know what's this one. Okay, so then we need the Maxwell relation. Okay, so if we start from something like TDS plus FDL. Okay, so then I can define something that is But we see now here we want to have L and the T as my independent variable. So what can I do? So I can have something that is E minus, maybe this is minus, plus, okay, I don't know the sign here right now, minus ST. So this one will have TDS plus FDL minus TDS minus SDT. So it's minus SDT and plus FDL. Okay, so then maybe I should have the minus sign here. Okay. Okay, so now this is related to so-called the Maxwell relation. Okay, but that is also very simple. That just means the second derivative commute. So here I see the d of the something is something minus SDT minus FL DL. So now if I take another derivative, so that means partial S partial L equal to partial F partial T. Okay, so now here I can replace this with FL partial S partial L. Okay, and we have shown that this is F divided by T, and which is minus K by L divided by T. Okay, so from those two, if I plug in, then basically I find minus L divided by T. So it's a negative number. So that means if I heat up the rubber band, it's going to contract. Okay. So those two are the rubber band simple model. So basically, the key concept is you try to understand something, the so-called entropic force, right? So when the system wants to maximize the entropy, then from outside point of view, it's going to have exert the force, okay, so that it can maximize the entropy. And then you can calculate this entropy function. Okay. Okay. So now there are another two homework problems that is related to the Euler relation and the Gibbs-Duhem relation. Okay. So what is the importance for this one? Those two homeworks. Okay. Okay, so as we mentioned many times, you should remember this from the energy conservation that dE is TdS minus PdV plus mu dN. So this, you can remember this equation from energy conservation. Okay. TdS basically is the dQ, right? Okay. So now I assume entropy is extensive. Okay, so now I have to emphasize that this is an extra assumption that usually it is valid, especially for large systems. Okay, and I know the energy conservation probably is a more fundamental conservation law, right? So even when the entropy function is not extensive, your energy conservation law should still be valid. Okay, but there are systems that this entropy function is not so extended. Okay, so what does this extensive mean? So that means if I scale everything by some alpha factor, okay. So if I increase my particle number, my volume, my energy by the same prefactor alpha, then I expect my entropy also scale by the same factor alpha. Okay, so this has very strong constraint on the form of the entropy function. Okay, so we consider the case when alpha is 1 plus some small number epsilon. Okay, so it's something like I'm going to take a derivative. Okay, so now if I plug in this, that means 1 plus epsilon s is something that s 1 plus epsilon n 1 plus epsilon v 1 plus epsilon e. Okay, then I'm going to just to show the detail related to one of the variable n. Okay, so I can do an expansion on this one. So this is something like s. Okay. Ooh. Okay, so I'm going to rearrange this. Okay, so if I only consider one variable, then what do I see? Okay, so let me just write down one variable case first. Right, so now if I only consider one variable, okay, so then it's straightforward to extend to 3 variables. Okay, so for one variable, that means S alpha n is alpha Sn. Okay, So now I subtract both the left and right by the same. Okay. Okay, so now if my alpha is 1 plus epsilon, then this is basically epsilon Sn. Okay. So now I divide this epsilon to the left hand side. Okay, so basically I have S m plus m epsilon minus Sn divided by n, and this would be Sn. Okay. And now I want to relate this to the partial derivative. Okay, so we see here like this change from n to n plus epsilon. Then, so then maybe if I get this and then this. So if I multiply it by this, so it's something I add entropy function by delta n, which is epsilon multiplied by n, and then divide by epsilon n. Okay, so in the limit of epsilon go to 0, then the left hand side becomes the n partial s partial n, and the right hand side become s. Okay, so now if I have other, then basically then other independent variable, then I can basically calculate the same thing, and then I got this. Okay, so this is Euler's relation. Okay, so remember that this valid only when the system is really extensive. Okay, so how do I connect to the another relation? Okay, so first I write this Euler relation. And I'm getting lazy, so I forget about the subscript that where the parameter that I should keep as a constant. Okay, so now I want to change those three partial derivatives to something else. Okay, so again we start from our lovely dn. De is tds minus pdv plus udn. So from here, this one I know I can rearrange it to ts is 1 over tde plus p divided by tdv minus u divided by tdn. So that means partial s partial e is 1 over t, partial s partial v is p divided by t, and partial s partial n is minus mu divided by n, right? So that means I can change this to n 1 over n minus mu 1 over t plus v p divided by t plus e 1 over t. Okay, so that I can rearrange this equation, then I get something e is ts minus pv plus un. Okay, so that's something different. Okay, so now if I perform DE on this equation, then I get two sets. One set is TDS minus PDB plus mu dn. Another set is SDT minus BDP plus ND mu. But from our lovely energy conservation, I know DE is equal to TDS plus PDB plus mu dn. So that means the others, the sum of our three terms must be 0. Okay, so that means S is 0 is STT minus VDP plus ND mu. Okay, so again, this I have to assume entropy okay. This assumption is usually valid, okay, but you should keep in mind there are certain situations in which this assumption is invalid. However, energy conservation is a deeper, more fundamental principle, and if you find something that violates the energy conservation, that usually means you miss some energy in your calculation, and that doesn't mean the energy conservation is wrong. Okay, so there are some relation that is more fundamental than others. Okay, so let me see. Okay, so that is more or less what I want to say for the homework part. Okay, so you should read for the exam. You should read the chapters covered in this exam and also the homework 1 to 4. Okay, so basically you want to understand the microcanonical number. Okay, so your entropy and your log of omega function. Okay, and the canonical ensemble, and I have this partition function, which is sum over okay, and the grand canonical partition function that include also the particle number. Okay, and you want to understand how those for example, from canonical ensemble, how do you connect it to the classical thermodynamic relations? Okay, and you should probably want to. Another thing is you want to maybe review a little bit about probability. How do you deal with the discrete and continuous probability? Okay. Okay, so now let's go to quantum. Let me see, what do I want to say here? Okay, so again, I still want to say something more about the density matrix in quantum mechanics. Okay, so now this time let's start from something that is in quantum microcanonical ensemble. No, not before. Okay. So if I have a classical system, okay, so if I have a certain state, okay, so I have an energy E, okay, and I have many different states. They have energy E, right? So, and I have how many? I have omega, right? So omega essentially counts how many states I have, okay? And so if it's a continued degree of freedom, then I can think about this as some kind of shell, energy shell. So basically you count the volume of this energy shell. And then we say the probability of Hs is a constant, right? So if the total volume is number of different states L, then this probability stays 1 over omega. Okay, so now let's just imagine a very simple example that I have 10 states. That has energy E, right? So my omega is 10, and my entropy is KB log 10. Okay. Okay, so if I want to calculate certain property O, which is a function of S, right? So what's the expectation value? Right, so that means I can sum over all possible state that is compatible with my energy, right? And I calculate the what's the probability for this state, and then multiply by the value of something I want to measure for this state. And since this is a microcanonical ensemble, then my probability is uniform. I have 1 over omega. Okay. So now what we want to do is we want to imagine what would change if now I consider a quantum system. Okay. So I have a given energy, E, right? So I have certain Hamiltonian H, right? So I can try to find the energy eigenstate. Okay, but I can have a degeneracy. So in microcanonical ensemble kind of point of view, that means I have more than one eigenstate that have the same energy. So I need to have some extra index that's called I, so they still have the same energy. So that again, let's talk 1, 2 to 10. So I have a 2. So basically energy E, I have a degeneracy like a 10. Okay. So what's the meaning of the microcanonical ensemble? that means I have a probability to get certain state. It's a constant. And it's 1 over omega. Okay. So now if I have a certain operator, I want to calculate the operator average. So what should I do? Okay. So then I have a two label. Okay. So if I operator, then if I have a certain eigenstate E1, so I can calculate the expectation value if my system is in E1. Okay. But now I have a 10 state that has a degeneracy, right, of a number of 10. So that means I'm not always in state E1. So I have a probability 1 over omega that is stay in E1. So then basically I should have two steps. The first step is kind of classical. So the first part is classical. So I sum over all possible state. And what's the probability of E1? Or probability of that state. Okay, so this is the classical probability. Okay, so now if my system is in certain EI, then the expectation value for this O operator, then I can do this quantum average. Okay, so we can, for any, if we consider quantum mechanics, then the expectation value of a certain variable can be written as, first you have a classical probability part, right? Then depend on how many possible state you have, right? So if you consider microcanonical example, then you have to count what's the degeneration level for that particular energy, right? And they have a uniform probability, so like each one of them has a uniform, like say 1 over omega. And then once you pick up the specific EI state, then the quantum, oh sorry, this is EI sandwich O operator. Okay, then you have a quantum expectation value. Okay, so now for this part, you should go back to your quantum mechanics and understand what is the meaning of a quantum expectation value. Okay. Okay, so now if you only have one term, okay, then you go back to, so the probability is 1. And there's no summation, and you have only your quantum expectation value. So this is the pure. Okay. So for pure state, okay, so first we understand this. Okay. Okay. So now I want to rewrite this expression into a density matrix. How do I do? So So this basically sum over I have a PI. And then I have a EIOEI. Okay, so then I can insert any complete basis alpha. Okay, then I can rewrite this as basically a trace of O and then sum over PI EI alpha. Okay, so I define this as my density matrix operator. Okay, so we just derived this from a microcanonical. In this case, my PI is 1 over omega. Okay, but then we can generalize this to other ensemble. Okay, so then that's very simple. For canonical ensemble, that just means my PI is exponential beta E. Right? Then I can sum over all different energy. Okay, so different ensemble mean I have sort of a different. So in general, I can think about I sum over certain probability with certain, for example, energy. Okay, and this is my Boltzmann way, and then this will give us a canonical ensemble, and then I can generalize this to grand canonical partition function. Okay, so I think the key point is to understand that you think about microcanonical ensemble and you have a 10 possible state. In quantum mechanics, that you mean you have a 10 degenerate state with the same eigenenergy. But the wave functions are different. So if you want to calculate the expectation value, then you have a two part. Then you have a classical probability that tell you how to pick up specific energy degenerate eigenstate. And once you pick the specific EI eigenstate, then you have to calculate the quantum expectation value, which conceptually also contains certain probability concept. But that probability concept has nothing to do with the classical probability part. Okay. So once you understand this decomposition, then it's just a way to rewrite the expression into the trace of your operator with the density matrix operator. And then this density matrix operator will involve this probability factor in front in your expression. Okay. Okay, so now let's take another 10 minutes break and be back at 3:20. Okay, so let's start. Okay, so now let's go back to quantum statistical mechanics. Okay, so now let's go back to Bose and the Fermi statistics. Okay, so the the most important thing is that if we go to quantum mechanics, then you are either boson or fermion. Okay, so that means you should if you have more than one particle, then you should either symmetrize or anti-symmetrize your wave function. Okay, so specifically, if you exchange okay, so you should review this part in your quantum mechanics book. So now if you exchange particle number 1 and 2, you should get a plus sign for boson and minus sign for fermion. Okay, so to deal with this, an important thing is sometimes it's more convenient to think in terms of so-called occupation basis. Okay, so what is the meaning of that? Okay, so you have a certain levels. So with a certain energy eigenstate. Okay, so I have many particle numbers. Okay, so basically I can imagine. So suppose I have 4 particles. Then I can imagine that I put my particle like this. That's one possibility. Or I can have okay. Okay, so then so here are 2 possible occupation representation for 4 particle states, right? Because this many body wave function, so that basically you have many particles. Okay, so then you first think about certain energy eigenlevel state, and then you want to fill those energy eigenstate with particles. Okay. So why do we want to have this use this picture? So basically for fermion, then the anti-symmetrization of your wave function lead to the Pauli exclusion principle, right? So if you 2 particle pole, they are on the same location where you swap those 2 particles, they go back to exactly the same location, but they should overall minus sign. So that means the wave function should be 0. Okay. So that means that for any energy level, the occupation number can only be 0 or 1. On the other hand, for bosons, the occupation number can be 0 to infinity. Okay, so that means for bosons, I can have a 4 bar. For a 4 particle state, I can collect. I can put all my particle into a single energy eigenstate. Yeah. And this will give you a certain crucial difference later. Yeah. And so it's more convenient to so now in the limit of a non-interacting boson and fermion. Okay. So remember that in the classical, if I write my Hamiltonian as a sum over individual Hamiltonian, non-interacting, okay, so the advantage for this is my partition function will be the product of the single kind of particle Hamiltonian particle partition function. Okay. So now, similarly, if I have a non-interacting bosons or fermions, okay, so I can imagine some Hamiltonian, now it's a quantum, that they can decouple into the individual ones. Okay. In this case, then I can imagine that, but now I have many particles. So now I'm actually working in the grand canonical ensemble. Okay. But I assume they are non-interacting, so I have uncoupled grand canonical ensemble. Okay. So if I have a certain eigenstate, but now this uncouple is between my different eigenstate. Okay. So this non-interacting fermion or boson, the grand canonical partition function can be written as a product of individual grand canonical partition function. And this K is the eigenstate index. Okay, so it depends on how you index your eigenstate. Okay, and then as we mentioned before, the crucial difference between boson and fermion is for boson, the n particle. Now, I only need to calculate the grand canonical partition function for a specific eigenstate K. And in this case, for boson, the n occupation number can from 0 to infinity. And fermion, my nk is 0 or 1. So that means for boson, my grand partition function for mode k, I can sum, then this is a grand partition function, so I can sum over all possible occupation number, which is 0 to infinity. Right? And then I have a specific thing, and my energy will be nk minus multiplied by ek, and I have a chemical potential mu. Okay, so this is essentially my grand canonical partition function for a single mole. Okay, so I can take out this common nk prefactor and factor. So ek minus mu to the power of nk. Okay, and this nk go from 0 to infinity. So I can have an exact sum of this series And usually we arrange this to be no, I don't need to. Okay. And my grand partition function, non-interactive boson, is the product of all different eigenmole, and for each eigenmole is 1 over 1 minus exponential beta ek minus mu. Okay. So my grand free energy which is defined as minus kbt log of my grand partition function, right? So we find that for the non-interacting boson, it becomes, I take a log, so this is, and this minus cancel this 1 over, so basically I have a product become a summation over k, and the kbt, I have a log 1 minus exponential minus beta ek minus mu. Okay. Okay, so one of the most important properties is to understand what's the average occupation number for mode K, which can be calculated by the partial derivative of grand partition function, grand free energy to respect to a chemical potential. And you carry out this calculation, you get and you simplify it, you get this important formula. Okay, so this is called the Bose-Einstein distribution. Okay, so first is 1 over exponential beta e minus mu, and the important thing is minus 1. Okay, so how do I get that? Okay, so in order for this to be meaningful, I see that, so this is for mode K. So I see that this chemical potential should be smaller than all the energy level. Okay, and when your chemical potential approach your lowest energy, then this factor big E for the ground state is E minus mu becomes 0, and this becomes 1 minus 1, and this occupation number becomes 1 divided by 0, so that goes to infinity. Okay, so that's sort of limiting case, and that is going to relate it to the Bose-Einstein condensation. Okay, so if you look at the formula, this tells you that occupation number can go from 0 to infinity. Okay, so now they have this important minus 1 factor. Okay, so on the other hand, for fermion, it's very different. So your NK can only be 0 or 1. Okay, so your fermion your one more grand partition function for fermion basically has only two terms. Nk to 0, you got 1. Nk to 1, you got exponential minus beta ek minus mu. Okay? And similarly, your grand partition function is the product of all single mode partition function. Okay, so now if you calculate the expectation value of your occupation number, your mode k, what you get is okay. So this is simple enough that I can this is your weight. So this is a partition function, and then you on the other hand you have nk multiplied by your weight. Okay, so there are not so many terms, you just write down all of them. So you get that the same exponential, but now you have plus 1. Okay, so how do I remember this is a plus 1? Because my occupational number can only be 0 to 1, right? So you have a plus 1 instead of a minus 1. If you have a minus 1, then your occupation number apparently can go larger than 1. Okay, so now you should have this as be about plus 1. Okay, so this is so-called the Fermi-Dirac distribution. Okay, and sometimes this with this so-called Fermi function. Okay, so you should have a rough idea how this function looks like. So there's a chemical potential mu here, and this is the e-axis, right? So when your energy is much larger than chemical potential, this exponential become very big, and this so your occupation number become very small. Okay, so right when this E equal to chemical potential, then you have a occupation number 1/2. So typically you have this kind of shape. Okay, and the function is only deviate from 0 or 1 in the range that is any range that is roughly kBt. Okay, and it's important that when the temperature goes to 0, then essentially you are going to get a delta function, that a step function that for all the state that has energy lower than chemical potential and it's occupied. For all the state that has energy larger than chemical potential is unoccupied. Okay. So in the classical mechanics, we talk about this Maxwell distribution. Okay. So then how do I get that here. Okay, so it's something like if we forget about the +1 or -1, then we get this exponential minus beta ek minus mu, which is the one we get in the classical mechanics. Okay, so in classical, we have this. Okay, so suppose I have a distinguishable classical particle. I have some omega function. Then I divide by the n factorial factor. Then I get the proper omega function for undistinguishable classical particles. Right? And similarly, if I get the partition function for the distinguishable n particle state, then I divide by n factorial. I get a partition function for the an undistinguishable classical particle. So for quantum, there is no such a particle because in reality, in quantum mechanics world, there should be only fermion or boson. Okay. So, but however, I can think about some bogus particle which obey this so-called Maxwell-Boltzmann statistics. Okay, so in the next, basically I just copy everything. So for n non-interacting, so sometimes this can be a good approximation. I want to have this. Okay, so maybe I don't want to go about here then. No. Okay. Okay, so maybe we should come back to this quantum Maxwell distribution later. Okay, so now today let's just sort of quickly go through some of the application of this quantum statistical mechanics. Okay, so typically one of the famous example is apply this to black body radiation. Okay, so here, one important thing is to calculate the density of state in omega space. So that is G omega. Okay, so here the energy is h bar omega k. Okay, so how do I, let me see. Okay, so I want to say a little bit more detail about this because it's related to our probability transformation formula. And again, if you use that delta function recipe, then it's easier to get the density of state somehow. Okay, so what is a black body radiation? So we can consider a box, which is L by L by L. Okay, so if you solve this electromagnetic wave inside this black body bus, okay, so with the boundary condition that this electric field at the boundary should be 0. Okay. Then this is kind of a standing wave, right? So basically, the E Hell has Ex, Ey, Ez. They have 3 components, and each component is a function of position and the time. Okay, so the solution will look like in time there was sine oscillation, and in space you will have okay. So if it is x component, then x is the cosine kx, while the other direction y and z is sine kyy and sine kzz. Okay, so now we know this boundary condition usually give us a quantization of a k vector. Okay, so if you know plug this equation and similarly for the other component, basically what you'll find is kx squared plus ky squared plus kz squared is omega squared divided by c squared. Okay, and on the other hand, kxl should be some integer multiplied by pi. Okay, so that means I can think about my omega square is something like a pi cl nx squared plus ny squared plus nz squared. Okay. Okay, so if I think about my L is very big, then this is sort almost like a continuous function. Okay, so now the question is, how do I get this density of state? Okay, so now the n, x, n, y, n, z you can think about is some kind of discrete. Okay, so you are in different way you can count this in a way that you feel comfortable. Then, but I just want to show you it's a sort of systematic and easy if you sort of use this delta function transformation. Okay, so you think about your some original space like either k or n. So it's n space. Basically, your every n I have a one state. Okay. 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 And if you want to normalize the probability, you should divide by some overall constant. But that's not the essential here in this delta function transformation. Okay, so basically I want to have the density of state in n space is 1. So what is this the density of state in the omega space? Okay. So basically I have the sum over all n, x, n, y, and z, right? And then what do I have? I have a delta. Okay. And I have this relation that okay, let's go back. So and C pi, okay. And I have that I have this probability. Now, if I think about this is discrete, then basically what I do is when omega I have some discrete delta function that ensure my omega square is pi c divided by L square nx square plus ny square nz square. Okay. Okay, so now there are some extra. Okay, so I have some certain polarization, so I get 1/2, and I have some factor. So this another factor coming from basically when I do this n square y ny square. If I put relative minus sign in front, basically my n square, which is defined as nx squared plus ny squared plus nz squared, is the same. Okay, so there are certain overall constant factors. Okay, so now, but this I can think about is a continuum. So continuum means basically you integrate over your space. So you can think about this 0 to infinity. Now you have a basic sphere. So it's m squared 4 pi n squared dn. Okay, but now since you are doing integral, then basically you should write this as a delta function, which can be written omega minus nc pi divided by L. Okay, and then you carry out this integration, you'll see this is a pi. Okay, so that gives you the density of a state in the omega space. Okay, so now for example, if you want to calculate the density of a state in the wavelength space, then you can carry out the same calculation, but now you have to, this delta function is now related to your wavelength, so then you will have other factors. Okay. Okay, so remember this probability transformation. So you can imagine like simple dice that you want to sum over x1 and x2 to s, right? So you have discrete sum over all x1 and x2, and then you have a chronic discrete delta function of s and x1 plus x2. Now, if you imagine you go to a continuum limit, then basically replace this summation by the integral, and this discrete delta function by a continuous delta function. Okay, and then you can get the result. Then this is also help you if you want to calculate the density of state for boson or fermion. And let me see. So maybe we can skip this part. For example, now similarly, if I quantize my particle in the box, right? So what I need to get is density of state for bosons. So for here, first from the particle in the box calculation, the energy level and the energy has these relations. Right? So I can write this as h bar squared pi squared 2ml squared m vector squared. Okay. Now I want to calculate density of a state in terms of energy. Okay. So that means in n space, but now this n cannot go to 0 and cannot go to minus here. Okay. But now, so I convert this summation to I want to in a continuous limit. Then what I can do is now this nx goes from 0 to infinity, ny goes from 0 to infinity, and nz goes from 0 to infinity. Okay, and what is my delta function transformation? I got energy, and how energy depend on my n vector. Okay, so now I can write this as 1 over a, and I go to a spherical coordinate, and this is 0 to infinity 4 pi n squared dn. And this is energy divided by h bar squared pi squared 2ml squared n squared. Okay, so now I need to do a change of variable, and this becomes x. Okay, so if you perform the change of a variable, what you'll find is you get some dimensional prefactor and a dimensionless integral. Okay, so that means by performing this integral, you get energy 1/2 with the prefactor. And we see this 1/2 will depend on the dimension of your integration. Here is 1/2 because we perform this nx, ny, nz on a 3D space, right? So now if you go to 2D or 4D or 1D, this integration will give you different result, and your density of state will be different. But you can still basically use this simple transformation formula to get your density of state. Okay. Okay, so I think I will stop here for today. So if you have a question about the material that will be covered in exam 1, you can email me and I'll try to answer to your questions. Okay, and we don't have other new homework for this week, so just please read the book and read the textbook and homeworks, and read your homework again, and if you have a question about your homework, and you can also email TA and to see how, and you can also check your grade for the homework on ILMS. Okay, so we almost finished the grading for the homework 1 and 2, and should finish the grading for homework 3 pretty soon. Okay, so before the exam next week, I'll email you the science sheet assignment, and let's hope you can prepare well the exam for the next week. Okay, so that's it for today, and let's see you next week during the exam.